Hello and welcome to the screencast on using constraint equations in optimization problems. A constrained optimization problem is a problem in which we want to make one particular quantity as large or small as possible, subject to one or more constraints. In this section, we'll focus on maximizing or minimizing quantities such as volume, surface area, or cost when considering boxes, tanks, cans, or other 3D containers. When we consider the volume and surface area of 3D containers, polynomial functions will frequently arise because these formulas fundamentally involve sums and products of variables. You're encouraged before working in this section on reviewing the different formulas for the surface area and volumes of common 3D shapes such as boxes and cylinders. As stated, a constrained optimization problem is a problem in which we want to make one particular quantity as large or small as possible, subject to one or more constraints. It is worth noting that a constraint is a limitation or a restriction. When constructing a 3D container, examples of constraints include the amount of material available to construct the container, which would be surface area, the amount of money available, or the required volume of the container. Containers may be boxes, cylindrical tanks, or cans, or other 3D shapes. Let's look at our first constrained optimization problem. A cylindrical can is being constructed so that the base and top of the can cost $3 per square foot, while the sides cost $2.50 per square foot. If we only want to spend $15 on materials for the can, how can we write the can's volume as a function of a single variable? So the first thing we want to do with these problems is always identify the constraint. And so here we saw we only want to spend $15 on materials for the can. So our constraint is cost. We only have $15, and cost is going to be related to the materials for the can, and the materials for the can are actually going to be related to surface area. So what we're going to need to do is find a formula for the surface area first, because we know how much it costs for different areas, right? When we see square feet, that's an area, so $3 per square foot for the sides and the top, bottom, and top. So we'll start out with the area. We have the top of the can is a circle. Pi r squared would give us the area of that circle. There's also a base with the same area, so we could really say we have two circles of area pi r squared, and then we need the area of the sides. Again, if you have reviewed the formulas for a cylinder, you'll remember that the formula for the side area is 2 pi r times h. So it's worth noting here, 2 pi r squared, that was the base and the top, and the 2 pi r h, that was the sides of the cylinder. And that's going to be relevant because the cost for the base and the top is $3 per square foot, so 2 pi r squared, that would give us the amount of square feet, and it's $3 per square foot, so we would multiply that together to get the cost of the base and the top. And then the sides cost $2.50 per square foot. 2 pi r h, r and h would give us the square feet, and that's $2.50 per square foot. So that would be the cost of the sides. And remember, we were constrained to only $15, so what we could really say for our constraint is 15 equals, and then I'm going to simplify a little, 6 pi r squared plus 5 pi r h. So this is our constraint, the cost of materials. Now we're not done. We were asked to write the can's volume as a function of a single variable. So the volume of a cylinder is the area of the base, pi r squared, times the height. So you'll notice right now the volume depends on two variables, r and h. And we want the volume to be a function of a single variable. So that's where the constraint is going to come in. You see that the constraint involves the exact same variables. So if we could solve for one of those variables, then we could replace it in our volume function. So we could solve for r or h. I notice there's an r in both terms of my constraint equation, so that would actually be rather challenging. It looks like there's only one h in the entire constraint equation, so it's probably easier to isolate h. So we would isolate h by taking 15 and subtracting 6 pi r squared, and then dividing both sides by 5 pi r. So 15 minus 6 pi r squared divided by 5 pi r equals h. So we can use this constraint equation to isolate one of the variables, and then we can substitute that into our volume function so that our volume will only depend on one variable. So we'll have pi r squared times 15 minus 6 pi r squared all over 5 pi r. And now our volume depends only on the radius. So technically, that is the volume as a function of a single variable. We have answered the question, but let's simplify this a little bit so we can see that this is actually indeed a polynomial function. So I'm going to start out by thinking pi r squared, that's over 1, so I can multiply that, distribute it into the parentheses, and we'd have 15 pi r squared minus 6 pi squared r to the 4th, all divided by 5 pi r. And then since everything's being divided by 5 pi r, we could actually think about this. 15 pi r squared divided by 5 pi r minus 6 pi squared r to the 4th divided by 5 pi r. And then from there, we could reduce, and we're going to get that the volume as a function of r. So we're going to have r is going to cancel out one of those. The pi's are going to cancel. 15 divided by 5 is 3. So we'll have 3r and then on to the other piece, pi squared divided by pi will be left with just a pi. R to the 4th divided by r will be left with r to the 3rd. So we'd have 3r minus 6/5 pi times r cubed. And this would be the simplified version for the volume as a function of r. And then it's a little easier to see this is a polynomial. We have two terms, 3r and negative 6/5 pi r cubed. It's also reassuring that we have a volume function, and the degree of that function is 3. Volume is cubic units, so this is a good sign that our degree is 3. In the following video, we'll determine the domain of this model, and we'll use this model to determine the dimensions of the cylindrical can with the greatest volume given the cost constraint.